Hello, and welcome to my instructions for building one of these. Come on, autofocus. Do the thing. Right. So my employer, Oxide Computer, is fully remote. And so once a year, we try to get everybody together so we can see each other's faces. And this year, I thought it'd be fun if we ran a surface mount soldering workshop so people could learn the basic techniques we use to build our computers, or at least the prototype boards for our computers. And to that end, I thought it would be particularly fun if we had people make something that at the end could wind up running Hubris, which is our real-time memory protected operating system that we wrote for our low-level firmware on the servers. So this is about the simplest circuit you can make that will run Hubris at the end, and it's made out of components that can be reasonably hand soldered by a beginner. We've had about 40 people work through this successfully, most of whom had little or no previous soldering experience. So if they can do it, so can you. So when you receive the board, if you get a kit from me, you get a board, you get a baggie of parts, which I've already dumped out over on my workbench over here out of frame. The bare board looks like this. So you'll notice if you get a kit from me, J2, the sticky outy thing at the bottom, already on there. That's because this part turned out to be really hard to hand solder. So if you make your own board, you're going to have to put J2 on it. I apologize about that in advance. It is doable. It just takes people, particularly who are new, a very long time. So all of the components on this board are surface mount, which in my opinion is a pretty reasonable place to start learning soldering nowadays because honestly, through-hole components, the old style are more work. So this is entirely surface mount, and that means we're going to need some surface mount assembly techniques, which is what this video is about. To complete this, you will need a kit, some tweezers. These are pointy curved end tweezers that are honestly very cheap and I got on the internet. A soldering iron. Doesn't super matter what kind of soldering iron, but it's important that you have a tip you're comfortable working with, and I'll say more about that in a minute, and that the iron can be temperature controlled for the right temperature for the solder you're working with. Normally nowadays that's lead-free solder, and you want to make sure your iron can be set to the right temperature for your solder. That'll make everything less frustrating. If you have an old school, like plug into the wall, no controls soldering iron like you might have gotten from Radio Shack 20 years ago, this is going to be a frustrating exercise, and I recommend looking for something slightly nicer. I've had people complete this with $35 soldering irons, so don't feel like you have to buy something really expensive. It just needs to be temperature controlled. Finally, you're going to need solder, and solder wick. So solder is what we put onto the board when we're soldering it. Obviously, solder wick is how we take the solder back off, which is very important for fixing our mistakes because you will make mistakes. I do, so maybe you won't. I'll be very impressed. So let's dive in. So to build this board, we need basically two techniques repeated over and over. So I'm going to show the first one by starting the assembly at the start of the instructions with C1. So I've mounted this in a vise. You could also set it on the table or tape it to the work surface if it moves around too much on you, but I like this little thing. And I'm going to be using a microscope so that I can point a camera through it. You can probably get away without using a fancy microscope, but having some kind of magnifier, like even a magnifying glass, would probably help. This is made out of 1206 components, which are relatively large by modern standards, but are still pretty small by human standards. Let me switch to the microscope so you can see what the heck I'm doing. All right, so here I've zoomed way the heck in on our board, and I'm looking at C1. This is C1. This is a capacitor. It's a surface mount component. Most of the things we're putting on the board are going to look very much like this. Now, they don't come naked like this. If you get a kit from me or if you buy from DigiKey, they're going to come in something called tape. Tape looks like this. Here's two capacitors still in tape. Now, tape is really intended to be opened by a robot, but we can open it as a person. So what we do is secure it with a finger, and with your tweezers kind of peck at this edge, because there's a plastic flap on the top that we're trying to remove. There, you see I got it? So now we can take the capacitor out. This, however, is a capacitor we need in a later step, so I'm going to set it back aside. So, C1, the first thing in the instructions. This is a capacitor on the voltage regulator. To solder this, we're going to use the technique that I suggest for basically all of the parts on this board, which is as follows. Zoom in just a touch. Okay. Step 1, take your soldering iron, take some solder. Rather than dragging a reel around like this, I suggest grabbing some solder wire and just ripping it off. So now you're holding a loose piece of shiny wire that you totally can't see on the camera, but pretend you can see it. So my soldering iron tip is not very tiny, but it ends in something called a hoof tip. That's the flat area on the end. But regardless of your tip geometry, what you want to do is put a little bit of solder on it. So now I've got a little bit of solder on it, and that'll help to conduct heat through to other things. And specifically, we want it to conduct heat through to this pad here on C1. So I'm going to start with this pad, which happens to be pointing toward my dominant hand, and feed some solder in, and you see how this melts. And now we take the iron off and it solidifies, and we have a blob of metal where we used to have a gold naked pad. So that's step 1. Step 2 is to grab your pair of tweezers, and grab your component, C1 here, and set it sort of where it needs to go-ish. And then with your iron, touch the blob of solder that you just laid down in the previous step. So it'll go molten, and then you slide your component over into the solder, take off the iron, and release the tweezers. So now the component is soldered to the board, the solder has set up, and the reason that the slide in was nice is because that kind of scoops the solder up onto the edge of the component, ensuring that it goes up onto the side of it and makes a good electrical connection. It's important at this point to make sure there's some of the other pad visible, because we're about to need to poke it with our iron. I've got a little too much of the pad visible, so just aesthetically, this doesn't matter electrically, but aesthetically, I'm going to center that a little bit better. That's a little bit better. Okay, great. This crap that you see building up on the board around here is flux. It came out of the solder. Most solder is what's called flux core solder. Flux is an amazing chemical that helps with your soldering, but also builds up like crap on your board. We'll clean it off later. So, with that joint done, I want to rotate the other joint down to where I can easily get to it with both hands. So here's solder in one hand and an iron in another hand. All of this is basically designed so you only need 2 hands, because I don't know about you, but I only have 2 hands. So now we're going to touch the pad and the component, kind of ram it into the corner where they meet, and then feed in some solder and remove the iron. So you could see the component, the solder wick up onto the component, which briefly went molten, and the pad obviously is no longer gold. That's a good sign. That means the solder flowed to cover the pad. So we have one successfully installed surface mount component, one of several. So now I'm going to switch to the other board and talk about what we do when we screw up, because I've prepared the other board with a mistake on it. Or, okay, well, let's make a worse mistake. So here's a nice mistake. Let's bridge some pins. So this thing labeled U2 here, this guy, black thing. This is our microprocessor. It has 8 pins. They all need to be soldered. They need to not be randomly soldered together by a clumsy person. So as a clumsy person, I will represent the clumsy person interests by putting a big blob of solder so that these 2 pins are now 1 pin. Whoops! So that's That's bad. We don't generally want to do that. They would like to be separate pins living their own lives. So, good news. We can fix this pretty easily, which is good because you're totally going to do this. So, this is solder wick. Usually comes in a reel, like the one you can see in the inset here. If you zoom in way close, it looks like this. It's a copper braid. There's no magic to it. Solder likes to go where the heat is for physics reasons. Copper conducts heat really well. So if we want the solder to not be on those pins anymore, what we do is we take some solder wick, we put it where the solder can get onto it, generally like right on top of the solder, then we mash it with the iron to heat it up. Watch this. Oh. So you see how the solder got drawn onto the copper, which was hotter than the pins, and the pins are now bare. In fact, the pins are so bare that this board might need the pins to be resoldered before it works, but we fixed our mistake. So that's how to put the solder on and how to take the solder off. Those are the two most important things. Other than that, it's mostly repetition and small variations. So let's switch back over to our unbuilt board. And continue with the assembly process. Okay, so we did C1. Now let's zoom out and talk about the instructions in order. So in the instructions, I have you build the board in blocks. And at the end of each block, we do a verification process to make sure we haven't screwed it up yet. And then to fix whatever it is that we did screw up. The first block is the voltage regulator. The voltage regulator is currently on the scope here. It consists of a voltage regulator chip, OBS, some capacitors that are needed to stabilize its input and output, and a USB connector, because USB is the de facto way of putting power into things nowadays. I thought it'd be convenient to just put a USB connector on here. So to get the power supply working, we need to install C1, C2, the regulator, U1, and then the USB power plug, which is J1. There's the label there. So let's do it. We're going to start with C2. So the C2 came in paper tape, which I've already cut up here. So the process for opening this is very similar to the plastic tape. It's just a little bit stickier. Here we go. Okay. Plastic flap removed. Part accessible. You can try to reach in here with the tweezers and grab it out at this point, but honestly, I just do this. Dump. Okay, it went over here. Let's get it back over here. These capacitors are not polarized. They're not sensitive to which way you put them in. In fact, this one's even sort of square in cross section. This one's skinnier. You can see it's got a skinny side and a fatter side. So the easy way to do it is like that, laying flat on the board. You could also stand it up on the skinny edge, but that sounds like work, and why would you do that? So we're going to repeat our process over again. Let's move C2 out of the way. I'll zoom in a little bit for those of you following along at home. We'll do this one in big. There we go. All right. So again, I'm cleaning my iron tip to get any sort of oxidation and crap from the last time off. I have a brass sponge for cleaning the tip, which I recommend over a wet plastic sponge. These destroy soldering irons. Brass tip cleaner is the thing to search for on the internet. So now I have a tip. It has no solder on it. I need to fix that. Let's put a little bit of solder on the tip to help it make contact. Boop. Okay. And then let's make contact with one of the pads of C2, chosen kind of arbitrarily, and feed solder and make a blob. Now we remove the iron and we have a blob with a bunch of flux next to it. So with setting down the solder and taking my other hand, I move C2 into position-ish, close enough. Heat up the blob of solder we just applied and slide C2 into place. Yep. And then remove the iron. People sometimes ask, like, oh, my hands aren't steady enough to do this kind of fine work. And honestly, My hands aren't steady either, and as you probably just noticed from me wiggling C2 everywhere. And also I just drank a big cup of coffee before I started this demo. Steady hands are a skill you can learn, which might be surprising, but is absolutely true. And in particular, magnification, like we have here with this microscope, helps a lot. The brain is really good at controlling the motion of your hands based on visual feedback. And if we use a magnifier to make that visual feedback bigger, like I'm doing right now, your brain can control smaller movements. It's kind of magic. This is true whether we're talking about a cheap jeweler's loupe or magnifying glass, or a fancy-ass microscope. Okay, C2 looks pretty good on both sides. I'm going to take a moment to do a zoomed-in view of those solder joints out of the vise, just to make a point about what it is we're looking for. So let's tilt C2 up so we can see it on the side. So each of these joints is fine. They're different in some important ways. You'll notice that one of them, the one to the right of the video, has kind of a point. That's a sign that we honestly have too much solder. And the point is where we drew the iron away. The solder got pulled into a little point. That's fine. The electrons won't care. The important thing is that, as you can see, the solder is, let me get a pointy thing to point with. Hello. The solder has flowed onto the pad. You see how it's sort of like a water droplet. The surface tension is holding it across the pad, and also flowed up onto the side of the part. This is what we want. The solder is bonding the metal end of the part to the metal pad on the board, which will make an electrical circuit and also hold it in place. On the other side of C2, we've got something pretty similar, but without the point, with less solder. And you can see it has flowed onto the pad, which is easy to tell on a board like this with gold-coated pads because you can't see the gold anymore. And it's also clearly climbed up the side of the capacitor. So that's what we want. These are totally acceptable joints, made with a shaky hand. Let me fit this back in the vise. The other thing that's important to note about hand stability during a process like this is that there are tricks for making your life easier. I'll talk about them on the regulator here. So I'm right-handed, and I prefer to hold the soldering iron in my right hand. You may feel differently. For me, I put the solder pad that I'm going to start with toward my dominant hand, which means I need to rotate this all the way around and then find U1 again. There's U1, now upside down. Okay, because I'm going to start with this smaller pad. It's almost always easiest to heat up a small pad than a big piece of copper like this. And we'll notice that when we start soldering it in a minute. But you want to try to tack the part down using an easy to solder pad like this one before you proceed to anything fancy. Let's get our regulator. The regulator came in tape. I'll show it here on the inset. It's a tiny little thing in a tiny plastic box that I'm sure autofocus is having a really hard time with. Sorry about that. So we are going to open it using the same process as always. Okay, plastic film removed, part revealed. Hello. This is our first integrated circuit going on the board. So like most integrated circuits, this one is picky about which way it goes, unlike our capacitors. However, it's also pretty much only goes one way because you want metal on metal when you solder a thing. Otherwise, what are you doing? So you can see it lines up with the footprint like this. 3 little pins on one side, 1 big tab on the other side. You could try to put it on a different way, but you'd be a smartass. So please don't do that. So with that in place, we're going to follow the same procedure as always. I grab my loose piece of solder and my iron. Let's move this guy out of the way a little bit. Okay. Put some solder on the tip. Pick a pad. I'm doing this one closest to me. Heat the pad with the iron. Make a blob of metal. Remove the iron. Perfect. So you may notice that I'm commenting on when I remove the iron. This is actually kind of important. So and this is the next trick for dealing with unsteady hands. When you start putting a part into position, you're going to be wiggling it around like that if you're anything like me, because your hands are not, a robot. So what we can do is use the solder to help us. So I'm going to touch the pad. You can see the solder become molten. Slide the part over until it's somewhere I'm happy with, and then as soon as it looks right to me, don't try to steady my tweezer hand, remove the iron. Now it's welded to the board. So I can wiggle it a little bit with tweezers, but in general, it's not moving unless I really try, and then I would break the part, so don't do that. So if you don't like where a part is, you can grab the part, you can heat up the solder, you can move it to somewhere you're happier with, and then when it's good, you lift up the iron, you don't let go. Now it's stuck in place. Perfect. So let's proceed to solder the other little pad. Okay, so that's flowed onto both the pin and the pad, so that's what we want to see. And now we have this big one. So we saw underneath the regulator that this copper gold pad on the PCB and this much larger one are the same piece of copper. It just goes straight under. They're also bonded inside the regulator. They're the same electrical circuit, but this is also how the regulator dumps heat if it needs to. Which means, since solder uses heat, when we go to heat this up, it's going to be harder. So what I recommend is put your iron on the pad, hang out for a bit, don't get too impatient, and then poke it with the solder, and eventually, there we go, eventually it gets hot enough that the solder wicks onto the pin. Don't rush that. It's going to take a little while to heat up, and that's okay. The part will tolerate the heat. Don't worry about being fast. The board will tolerate the heat. This is part of why it's important to have a temperature-controlled iron. So those 3 pins look pretty good. I'll talk about what we're looking for there in just a second, but let's do the tab first. Because the tab is electrically the same circuit as that pin we just did, we don't technically have to solder the tab. However, it's good for both mechanical stability so that the part can't lift up and bend, and also as a backup electrical connection. So let's do the same thing. We got some solder on the pad, getting hot. We're trying to touch both the tab on the part and the pad with the iron simultaneously. And then we can try to put solder on the pad, or on the tab, excuse me, which is not yet hot enough to melt. Oh, now it is. Great. We're getting some flow. Great. Okay, look at that. And then we remove the iron. So we have a blob of solder that has flowed onto both the tab, now I'm pointing with the solder, and the pad. If we hadn't waited for that to heat up, the solder wouldn't have flowed as nicely onto both pieces, and we would have a potential defect later. So here's U1. Let's check this over before we do anything else. So I'm going to zoom in further because I can. So squinting at this through a magnifier, what we're basically looking for is, are these pads still separate? They started out separate. They need to be kept separate. We're not going to bridge them like we did with the pins on the microcontroller earlier for the demo. So in between the pads, we can see the black solder mask, and we don't see any shiny bits. Well, I don't see any shiny bits. So the problem here is it's covered in flux now. So everything's kind of shiny. So this is a point where I find it valuable to take the thing out of whatever you're using for work holding and tilt it up and look at it from an angle. Kind of wiggle it around. So you see how the areas in between the pads are not shiny silver. They're shiny because they're covered in flux. This is what we want to see. We're also going to double check this electrically in the next step after we put the USB connector on. So the most common mistake to have made at this point in the assembly is joining these pads together or failing to flow the solder completely from the pin onto the pad. So now we need to do the USB connector. So the USB connector is kind of cool. It's the biggest thing we've soldered so far. It's, human scale. You can actually see it on the inset here. It's the same USB connector you've used on everything for the past however many years. It sits in these two little holes on either side so that the pins line up with those gold pads. And it's press fit. So you get it kind of lined up, and then you press on it with your finger, or in my case with my finger, dunk, and now it's on there. And so if we can focus, you see the pins are really nicely sitting on their pads. Everything looks really nice. I can see, because I'm looking at an angle, that they are sitting flush. They're not like lifting up off of the pad. So this looks great. You'll notice that I mounted this without putting a blob of solder, and I didn't do the slide into it thing. That's because it's kind of hard to press fit a connector on top of a blob of solder. You want the board to be flat when you press fit a connector like this. So we can't have already made a mound of solder, because then the pins would sit on top of that mound of solder and wouldn't make it flush to the board. That would make the rest of them hard to solder. So don't do that. Instead, what we're going to do is, making sure there's a bit of solder on my iron, we're going to come in, heat a pad. I picked this one because it's the top one, and I don't know, that seemed fun at the time. And get the iron so it's touching both the pad and the pin of the connector at the same time. And then feed solder over here onto the pin and the pad, not onto the iron. Great. And then remove the iron. So that's probably a little bit too much solder, but it's a demo. That looks fine to me from here. We'll take an oblique look at it once I'm done with all of the joints. And then we just proceed to do all the rest of them the same way. Great. So we have to pop this out of our work holding because there's a thing we need to do on the back, but let's use that opportunity to have a look at it at an angle. So that's what the joints look like with the solder correctly flowed from the pad onto the pin. See how it's a nice smooth blob of metal. No bridges in between. This one's harder to bridge than U1 because the pins are kind of far away, but this is what we want it to look like. So this connector has retention tabs. It's pretty common for connectors like this to keep you from tearing them off the board in a fit of rage. You can see the pins that we press fit have come through here and are sticking out of these little gold ovals. What we have to do now is to solder those together. This is not important electrically. Well, okay, technically for USB it kind of is important electrically, but the main thing we're doing here is just mechanical strength for retention. So, tin my iron a bit, touch it to the gold thing. This takes a little while to heat up because it's a big piece of metal. Also, do not use your finger on the USB connector to stabilize the board right now. The USB connector is going to get warm. See if we're hot enough. Right, so what I recommend is leaving the iron in one place, poke the other bits of metal with the solder. This tells you if they're hot enough yet. Whoops. In my case, they're getting hot enough. This will take a little while to heat up, be patient. Once they're hot enough, you can flow solder like that. Now we have a nice little joint. Now we need to repeat that for the next guy. My iron is still wet from the last joint, so I'm going to go ahead and just drop it on there directly. This one will probably heat up faster because the two are connected by a plane of copper. So they're actually transferring heat between each other. If you have a finger on the board right now, you'll notice the entire board is getting hot. That's because the copper planes in the printed circuit board are heating up from the iron. Okay, so that's two mechanical retention tabs that look pretty good. So now we have a USB connector. So at this point, we can actually test our work. I'm a big fan of testing things at the block level. So I'm going to, in our instructions, it specifies test across C3. So the first thing we're going to do is test for a short circuit. A short circuit could happen if we messed up our soldering in particular. So for this, we are going to use the resistance mode of a meter. And I'm showing the symbol on my old Radio Shack meter because the symbol on your meter is going to look similar. This first thing, the V with the dots over it, is DC voltage. We'll use that later. And then the ohm symbol is resistance. Do not use the beepy continuity mode of your meter that beeps if two things are connected. I'll talk about why in just a moment. All right, so our probe points are C3 here. So take the two probes, doesn't matter which ones at this stage, and poke one on one gold pad and one on the other gold pad and see what the meter says. It may take some pressure to break through a surface oxidation on the pads and make electrical contact. So right now my meter says 809 ohms. So that's what we expect in this case, empirically, because the voltage regulator chip is trying to regulate any current that we pass through and will show up as a non-zero resistance. But it also won't show up as a super high resistance, which means that the continuity beeping mode on your meter will misfire. 800 ohms is usually conductive enough for the meter to beep and report continuity, which is why it's misleading to use the continuity mode when testing things like this. So use the resistance mode. We're looking for about 800 ohms, plus or minus. So it seems like we soldered this correctly without any short circuits, which is great. What we need to do now, which I'm going to do a little bit off camera, but I'm taking this and I'm plugging it into my USB port over here. And I suggest plugging it into a computer rather than like a phone charger, because computers tend to be pretty good about cutting power if you pull too much current, whereas phone chargers will tend to just catch fire. And we already determined we didn't have a short circuit, so we probably won't catch fire, but that probably is doing a lot of work. Okay, so setting the meter back to DC voltage mode, the V with dots over its symbol, which appears to be a bit of a standard. We take our probes. We're going to poke C3 again. And I see 3.30 volts. 3.3 volts is what we want. You'll see somewhere, if this is working correctly, between 3.2 and 3.4. Anything in that range is great. You might also see negative 3.3 volts. This is also probably fine. So if you look at C3, where we're probing across, C3 is not like a dedicated voltage probey point. There's going to be a capacitor on there later. It just happens to be conveniently between the 3.3 voltage rail here and ground here. So when we sample voltage across this, we get 3.3 volts. If we have the positive or red probe on the positive side and the ground or black probe on the negative side, 3.3 volts. If we switch them and put the red on the ground and the black on the positive, we get negative volts, which is fine. If you see a negative reading, just check that your probes are backwards and move on. Don't worry about it. It's not going to hurt anything. Great. So we have a working power supply at this point. Next, we're going to dive straight in and see if we can't get the microcontroller working. Here's our microcontroller, U2. So I'm going to collect the next batch of parts from the kit. So we will start with the processor itself. Here it is. So this is what's called an SOIC 8 package, small outline integrated circuit. That name is a reminder. Don't ever call something small if progress might continue after you make it, because this is actually quite large by modern standards. I chose it because its pin spacing at 1 millimeter and change is coarse enough that we can easily hand solder it. Also, there's only 8 pins, which, given that we're doing this manually, is going to make it a lot quicker. So it wants to go here. There's a tiny ST logo on the package. It's easy to see with magnification. It's really hard to see without. So that's the ST logo. The ST logo is what marks pin 1. Also, you'll notice this is not an optical illusion. The bevel on this side, which shows up slightly dark in the reflection of the microscope lights, is slightly thicker. So we want the ST logo and the bevel to go on this side marked with the circle. The circle here is the pin 1 indicator. So other companies will put like an embossed or recessed circle on pin 1 so you can see it from a distance. ST doesn't like us that much. So let's move the chip out of the way and do the same thing we've been doing. I've got the board out of the vise right now just to simplify moving it around and showing you things, but that means it's going to try to move around when we solder. So this is hard to see with the light on, but if I turn the light off and you look at the inset, I'm using a pinky finger on the corner of the board to pin it down, and then using the rest of my hand to move the iron into place. You may or may not find this comfortable. It's what I do. You could also tape it down to your workstation or do any number of other things. Great, so we have a blob of solder on a pin. Doesn't super matter which one. Now, I'm going to grab the chip. And our goal here is to have each of these metal pins on one metal pad, not on 2 metal pads, not on 0 metal pads. We also need to make sure that there's some of the pad visible outside of the chip's outline so we can get to it with the iron. So let's try that. Melt the solder, slide the chip over. It's a little south of where I want it. Release the iron. So that's pretty okay. It's a little bit crooked. I don't know if you can see it. Let's see if I can do better. Okay, that'll do. So the pins are more or less on the pads. It's a little hard to see because of the automatic exposure on the camera. It's a little blown out, but you can see they're sitting on top of the gold pads, which is what we want. This, incidentally, is why it's not in the vise right now, because I couldn't do this. And they're sticking out a little bit on some sides. You can see if I tilt this way, but that's okay. As long as they're not bridged, everything's fine. So now that we have one pin tacked down, the chip is actually pretty mobile. I'm not going to show you by poking it because I'm worried I'll damage it, but if you bump the chip too hard right now, you will tear this pin off. So immediately, before I can make a mistake, I'm going to rotate the board so I can get to this pin on the opposite side. I'm going to take my solder and my iron. So it's important to get both the pad and the pin as always. So I kind of cram the iron in to the corner of the two. And you see the chip is moving and the chip is not hot enough for the solder to flow. Okay, move the iron in a little bit closer and be patient. Aha. There we go. That's what we want to see. So I applied the solder to the pin, but because I was heating the pin in the pad, you can see, let me close up for you. You can see it flowed to contact the pad as well. It's not just sitting on top of the pin, as opposed to the one next to it, which is just sitting on the pad. In fact, let me solder that one incorrectly to show you what it looks like. Okay, there's our pin. I'm zoomed way the heck in right now. So I get some thinner solder just to make sure I do this correctly, if you will. So what I'm going to do is I'm going to heat only the pin. I'm going to put some solder on the pin. Great. There, I soldered it, right? No, I didn't. So if we look closely, sorry about the focus, there's some solder on top of the pin, and it doesn't flow onto the pad, or at least not very well. The pad is still gold, the pin is just sitting on it. This is bad. This means we need to do it again. We don't need to take that solder off. It's not hurting anything. but we want the solder to flow onto the gold pad as well as the pin. That's how we make contact. So if I poke the iron into the crook of the two like that, sometimes that's enough to just fix the problem, but just for the heck of it, I'm going to put some more solder on and get it back in focus. Sorry about that. Great. So you'll notice by accident, I accidentally crapped some solder onto the next pin over. Whoops. We'll fix that in a moment. Generally speaking, if you have solder somewhere you don't want it, you take the iron and you poke it. So like I can basically comb it with the, there. So now it melted and it's just stuck to the pin. So we've done the bad soldering thing where the pin has solder and the pad doesn't. That's fine. If I poke the pad as well and get it real nice and hot, and then come in with my solder from an angle so that I don't touch the soldering iron tip by accident. There we go. Did that do it? I see some gold behind the pin, so that's not guaranteed to be good. Yeah, so the pin is still just sitting on top of the pad. So often the easiest way to fix this is to take the iron and just mash the pin down against the pad. Give it a few seconds so they both get real warm, and then pull the iron away. So what that should have done is ensure that they're in physical contact, and then transfer enough heat that they're both hot. And again, solder likes to go where it's hot. So let me get a real oblique angle here just to verify that we've done that right. Okay, so I don't see any gold from the pad sticking out. It looks flowed. There's a little bit too much solder on there. You can see the little peak I've drawn. Sorry about the reflections. The solder ends in a little bit of a peak. That's not necessary, but it also won't hurt anything. So we should be good to go. Now we do the other pins, which I'm going to do quicker without quite as much commentary. The pins on the end are easiest because you can get the solder up against it without hitting the iron. So that's nice. So as before, I'm rotating the piece so that I can get to everything easily with the iron. This is so much easier than trying to come around like from the back and bend around a corner and get things with the iron, particularly if, like this one, your tip is, I mean, you'll notice the tip is actually larger than the pins we're soldering. So we're not going to be super precise. It's important to have the piece work with us instead of fight us. Okay, so that's, I had to put a little bit of solder on the tip there to get that to conduct, and then there we go. That looks good. Next. Whoops. Okay, so this is pretty common. I accidentally poked my iron and now there's a blob of solder on my iron. So I'm going to clean my tip. And we're going to try it again. There. Okay. And last but not least. Okay. So that looks pretty good. If we do an oblique view, let's check that pin on the end, which looks a little bit suspicious. Yeah, so that pin on the end, which I think is the first one I tacked down, is a little bit kind of just sitting on top of the solder. Again, this is something we can fix pretty easily by mashing it with the soldering iron. Mashing things with the soldering iron cures a lot of evils. Mash. Give it a minute to heat up in its new mashed position. Take the iron away. Okay, now it kind of blends smoothly into the pad. That's what we want to see. All of these pins look good. I can see black between them as I wiggle it back and forth instead of shiny silver. The flux is distracting, but ignore it. That's why I'm wiggling it, so the flux will blink in and out as the reflection moves. So this looks good. So that's our microprocessor. In order to actually run this, we need what's called a decoupling cap. So decoupling caps are basically local stores of charge, sort of like a tiny battery, to make sure that if the processor suddenly needs a burst of power, it can pull it out of the cap instead of having to pull it all the way from your USB port, basically. So the decoupling caps, incidentally, were the piece of plastic tape that I opened earlier as a demo. So I'm going to dump one out here. Here's one. Awesome. Let's see if I can get that a little better in focus. Okay, so clean my tip, grab my solder and my iron, put a little bit of solder on the tip, boop. Now we're going to heat the pad. Same thing we've done before. Make a pile of solder, remove the iron. Figure out where my tweezers went. Here they are. Grab our little buddy C3. You notice the board is wobbly. It's because I'm not stabilizing it or putting it in work holding. I will fix that in a moment. Whoop. Heat up the solder. Slide C3 into it. Remove the iron. So we've got the top side of C3 done. Now we need to do the bottom. Now again, this style of cap, which is the one I've used throughout the board, is not polarized. So you can put it in either way, which is good because there's no markings on it to help you know which way is which, nor are there markings to tell you what kind of capacitor it is. If you drop one of these, it's gone. Just treat it as dead because you're going to find it on the floor, and it might be one you dropped earlier of a different value, and there's no markings on it, and life is too short. I always buy a couple of spares because they're a fraction of a penny each. Speaking of things that are polarized and have bad markings, though, now we need to do the LED. So I always try to put an LED on a microcontroller board because it's like the easiest thing to get working. And easy is nice. You don't need a lot of code working to blink an LED, which is why it's a popular demo in embedded. So our LED also comes in tape. You'll notice this tape is black. So that's because this is conductive plastic. Things coming in black plastic almost always means that they are static sensitive. So we'll want to be slightly careful here. Don't rub your feet on the carpet and then mess with this. In practice, I don't think I've ever destroyed an LED with static, but you could be the first, so be careful. In my case, this is an anti-static bench. I'm connected to it. I don't really have to worry. So using my gigantic hands, I'm going to grab the tape, get that little plastic flap off. Come on. Plastic flap removed. And here's a little, let's see if I can get that out this way. Nope, I'm just going to dump it. Dump, okay. It rolled away, you can't see it, it's over here. There's our LED. So, LED. LEDs are diodes. Diodes are polarized devices. They have an anode and a cathode. If you put them in the wrong way, they will, at best, not work. At worst, they will explode. Literally. So, let me zoom in on this guy. On the circuit board, I've marked which way the cathode needs to go using two different conventions. One is this diode, which is this triangle rather, which is intended to mirror the schematic symbol used for a diode on an electrical schematic, which points from the anode to the cathode. There's also a cup symbol around the cathode. This is KiCad's convention, and well, I don't love it, which is why I put a triangle on there too. The diode itself, how can we tell which way is the anode and which way is the cathode? You can see there's some stripes and different, like what's this C-shaped green stripe on this side, and then there's another green stripe over here, but it's very thin. And then like there's some copper in there with the tiny little like actual die bonded to it and a tiny wire because integrated circuits are crazy. So how can we tell which side's the cathode? The answer is you can't. You have to read the data sheet. Every manufacturer marks these differently. Different batches of the same one are sometimes marked differently. I don't know why this is okay. It's super annoying, but I read the data sheet for this LED, And I know that this side with the little C-shaped green stripe is our cathode, which means that this is actually backwards from how it needs to be. So let's flip it around. And nudging it with our tweezers. There. It wants to go that way. Also, LEDs hate to be anthropomorphized, so be very careful. So before trying to solder that, I'm going to save myself some frustration and mount this back in my vise. So which means I'll need to refocus. Sorry about the momentary blurriness. Okay. Okay, we're back to D1. Here's D1's footprint. Look at that. I like this matte black solder mask that I had the boards fabricated in, by the way, because like if you look here, it's really easy to see that there's a trace connected to this pad that goes over here, and like, I don't know, I just think it's really fetching with the gold. Anyway, enough about my aesthetic preferences. Here's our diode. That's the right way around. See, because we got our it'd be great if they all had this C for cathode, like consistently, but they don't get lulled into a false sense of security here. So I'm going to set that near where it goes and do the same thing we've been doing. Making sure there's a little bit of solder on the tip of my iron. I'm going to heat up this pad. Doesn't really matter which. I'm doing this one because it's closest to my dominant hand. Whoop! Pile of solder. Yay. Now that my left hand is free, grab the tweezers, grab the LED, set it on the board. One of the easy mistakes to make here is to grab the part such that it's floating off the board, which will make the sliding into the solder not work very well. So sometimes I'll drop it and then like re-grab it real gentle like to make sure my tweezers aren't lifting it off the board. Okay, so heat up the solder. Slide the diode over, release the iron. So you'll notice the gold contact on the end of the LED is now shiny silver from our solder. That's what we want to see. The solder has flowed well here. Now, trying not to give you motion sickness, I will rotate. Sorry for those of you in the audience prone to motion sickness. I myself am prone to motion sickness, so I feel for you. Microscopes are easier if you're the one moving things than if some rando on the internet pretending to be an electrical engineer is moving things on your behalf. Okay, so touching both the LED and the pad, I'm feeding solder in and I'm waiting to see it flow on top of the there we go. So that has definitely flowed onto the LED and the pad. So we have an LED. The next step in the instructions is to install the current limiting resistor for the LED, which, if we follow the trace, is just downhill over here, R1. R1 comes in paper tape. It's marked, which is great. Resistors are marked, unlike capacitors. Why the capacitor industry hates us all, I'll never know. So this is marked 221, which is surface mount convention for, well, it's actually 22 times 10 to the first, so 220 ohm. Anyway, you can Google it if you need to look up a marking like that. But this way, if you drop one, you'll know which one it is when you pick it up, which is great. I'm still going to try not to drop this one, because hunting around the floor makes for bad video. These paper tapes, again, are a little bit harder to open. I'm going to use the other way of opening this. So here's the secret way. So this is plastic on the front, paper on the back, like a shitty mullet. What you can do is actually poke this with your tweezers until it pops through. There we go. So now, if I can get this to show you the back side, I've punched a hole in the back of the tape and the resistor is sticking out of it. So the easiest way to get that out of there is actually to dump it. There we go. Great, discard the paper. Now, this is the underside of the resistor. It's being indecent. We need to flip it over. Great. So there's our resistor. So like the capacitors we've been using, this is an unpolarized component. It doesn't matter which way it goes. However, for aesthetic reasons, I'm going to make the letters or the numbers go the same way as the lettering on the board. I think that looks better. The electrons don't care. You can be a contrarian and punk yours up and put it upside down if you want. I won't judge you. So now my shaky hands come in, move the resistor. Solder on the iron, iron on the pad, solder on the pad. So to stabilize my hand, what I'll often do is hold my tweezers like a pencil so that I can rest the meaty part of my hand, my pinky finger and stuff, on the desk, which as you can see makes it easier, well, as I'm shaking, easier to hold the thing steady. Okay, so now I'm going to grab this, go in with my iron, move it into place, remove the iron. Fantastic. Just going to go ahead and do this without rotating the piece, despite my advice earlier, because, well, it's a lot faster with the video going. Okay, we have a diode, we have a current limiting resistor. Other things we need to get this working, we've got our microprocessor and its decoupling cap, we've got the programming connector, which I installed previously because it's a pain to do it by hand. If you're curious, I did this using solder paste and a hot plate, because the pins are all up underneath it and are really hard to get to with an iron, and they're difficult to see if you've done it correctly. So let's not for the video. I might make an add-on video showing how to do this with paste. Right, so this is actually enough of the circuit in place that we could test the microprocessor, put some code on it and see if the light blinks. So because that's a completely different workbench setup than what I'm doing now, I will cut away to me doing this later. So now that we have the microcontroller in place on our board, we need to test it and see if it works. So I have our board. People paying close attention will notice this board is actually at a later stage of assembly because I'm doing this segment after the rest of the assembly video, but the results will be the same. So this is the procedure that you can follow. I also have I have a SWID, serial wire debug interface. This is the current standard for talking to ARM processors. This particular one is from a vendor, and I don't recommend that you buy this particular one. It's just the one I have available. So, having already checked for short circuits on our board, it's safe to go ahead and just plug it into the USB port. Ta-da! Okay, it's not doing anything, which is what we expect. We haven't told it to do anything. So, with our debug probe, we grab our SWT cable and we seat it on J2. It only fits one way around. There's a key on it, so I mean, if you push hard enough, you can break it, but don't do that. So now we've got it connected. We've got our debug probe connected by USB to my computer here. So at this point, in our previously configured Hubris and Humility installation, we can run Humility probe. Ooh, wow, there's a lot of crap. So if we scroll up, so Humility probe looks for a debug probe, reaches out and dumps information about the CPU that it finds. And in this case, it's saying it found an ARM Cortex-M0 Plus core, specifically an STM32G0 mumble, and a bunch more crap. So that's great. That means our processor is actually running enough to talk to the debug probe. So what do we do now? Well, it'd sure be nice to have some code on the processor to see if our LED works. To do that, we run in the Hubris checkout. So we're going to flash the application defined by this TOML file. And it'll sit here and chew for a bit, and then, oh, okay. Okay, we've got an error reported, but that's okay. Tolerate that. So with that done, what's our board doing? Our board is doing nothing. Why is our board doing nothing? Well, on certain ST microcontrollers using the Humility toolset, you have to power cycle the microcontroller before you're able to run code the first time that it's flashed. We can power cycle the microcontroller by pulling it out and putting it back in. Oh, hey! We've got our light blinking at 1 Hertz. That's exactly what we expect from this demo application. That means that everything's probably working. The CPU is up and doing stuff. And if we switch back over to humility, we ought to be able to, well, actually it'd be easier to do cargo x task humility with our application config tasks. Okay, see, I haven't done this in a while. Okay, so humility has started up and has listed the tasks in our demo application and talked about what they're doing. So this is a working Hubris installation at this point. So at this point we can disconnect it from power, disconnect our debug probe, and resume our assembly, which will be the parts that are already here, but pretend you didn't see that. So now that the microprocessor works, the next thing in the instructions is a reset switch. So reset switches are really nice to have if your code is wrong. And I don't know about you, but my code is often wrong. So the reset switch is sort of our ultimate way of getting the processor to do what we want by resetting it. An embedded system without a reset switch is a user hostile embedded system. So the reset switch has a capacitor across it. This is an ST recommendation. I haven't totally thought through the electrical implications. I just saw this in the datasheet and copied it. That being said, I'm pretty sure what it's doing is eliminating pulses, transient pulses on the reset line and slowing down the edge, the transition from one state to another when the switch is pressed. So I've dumped out of the plastic tape our capacitor. This is the other decoupling cap. It's just like C3. Now I can't really solder in this orientation, so I'm going to rotate. Okay, C4, upside down, but it doesn't know. That's a joke. It's just because the letters are upside. Anyway, bear with me. So, solder on the iron, iron on the board, solder on the board. Tweezers, grab our capacitor, heat up the solder, slide the component in, release the iron. Great. Solder the other side, capacitor's done. So, before we get too proud of ourselves, I will warn you, the reset switch is actually one of the hardest components on this board. And that's because, in part, I made a layout mistake. So on most of these parts, I deliberately, let's go back over to U1, our regulator, actually. I deliberately used pads that were much too large on the printed circuit board. So you'll notice how there's a bunch of pad. This is where the pin actually ends. So there's a bunch of pads sticking out here. You may recall there was a bunch of pads sticking out here. That's really nice for hand soldering. It's really bad for density. So surface mount footprints intended for use in higher density things, which is most electronics these days, don't leave extra metal like that. This reset switch footprint is one of my high density footprints. So sorry about that. The good news is we'll get to talk about how to solder higher density footprints. Unfortunately, due to technical difficulties, I lost the sequence of video where I soldered the reset switch. So I've started with a bare board here so that I can walk you through soldering the reset switch, and then we'll cut back to the original board. So here is the reset switch footprint. Da, 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 da. Let me get a reset switch. Okay. So this switch, when installed, is going to completely obscure the footprint and basically hide the gold pads, like so. to a greater degree than our other components. This doesn't lend itself well to hand soldering. So the other reason this is kind of crappy for hand soldering is if you look at it from the underside, this is what's called a J-lead component. So rather than sticky outy pins that are convenient for us, the pads on this actually wrap around the underside. So that makes them hard to solder. We can't solder something we can't see. Fortunately, they do come up the side a bit, so we can get to them with the iron, but that's the basic problem. So let me show you how to handle that. As soon as I get the scope focused. Okay. Starting with our switch nearby, I'm going to start out the same way that we've been starting out, by tending the iron slightly and then applying solder to a pad. Oh goodness, so the pad is small enough that there was enough solder on the iron to do a convincing job of that all on its own. In fact, the iron is kind of sucking the solder off of that pad. This'll do though. So with our pile of solder, we then take the tweezers in our other hand, which is easier if you're not looking at the computer screen. My bad. And heat up the pad we tend and slide the component into place such that we can see solder or see pads visible on the other side. Now, it's really easy to get this lifted up off the board. So what I do is I press here and then reflow the solder just to make sure that it's all the way down. Let's see if I succeeded. So if we look at it in an oblique view, zoom way the heck in. Here's our joint. Yeah, so this looks pretty okay. The gold pad underneath is obscured. It's completely covered with the solder, and the solder travels up onto the J-lead on the side. Now you notice that you can see the top of the lead, and you can see a peak in the solder, and those are not the same. I'm a little worried about that, so I'm going to use the iron to reheat the part and see if I can eliminate that little glitch. So you can't even see the glitch from above, except that we can see that the end of the component lead is visible and is not solder colored. Okay, so stabilizing the part with my tweezers. I'm just going to rest the iron here to get everything real hot. Okay. Oof. And that looks better to me. It's about as good as we can expect on a J-lead like this. So we can see pads exposed on the other 3 pins, so I think we're good to proceed. I would recommend doing the pin diagonally across next for mechanical stability. You can see how the switch is a little bit crooked. That's okay. So, as usual, we want to touch both the pin and the pad with the tip of our iron, like so. And then once things are hot, feed some solder in. Things are not heating up. This is probably because I didn't put any solder on the tip of my iron to begin with. Let me remedy that. Okay. Yeah, that's much better. Now we got a blob of solder. We can't see the lead anymore. We can't see the pad. Things are probably good. Let's carry on. Poke. This one I'm coming in from the side because I can see some exposed pad. There we go. And then one more on the other side. There it is, shiny and gold. Oop, my iron has too much old solder on it for me to do that precisely. So, stabilizing the board with my hand, heat up the pad, feed in some solder, draw the iron away. Great. I think that's probably okay, but just to double check, we're gonna look at it at an angle again. So, a very blurry angle in one moment. There we are. Okay, so the pads are underneath the part, making it a little bit hard to tell, but these look okay. It so happens that this particular switch, 2 of the pads are redundant, so if we got them wrong, it'll probably still work. So that's nice. Okay, now we have an installed reset switch, and I'll cut back to the original video. So the final thing we have to do is this connector. There's these pull-ups here marked as optional. They're not optional in the sense of like you do these and you get extra credit. No, they're optional in the sense that if you put them on, the board won't work with other things. So the other things are, this is a connector used by Adafruit and SparkFun to make little I2C evaluation boards. It looks like this. So by putting this on here, it's wired up to the I2C interface on the microcontroller. And we can use this to then plug in things we buy from Adafruit or SparkFun, evaluation boards for new kinds of components we want to try out, and then poke them through Hubris. So that's what makes this board slightly useful instead of simply blinking an LED. So this connector is a little bit tricky. So this is the finest pitch of anything that we've worked with so far. It's 1 millimeter between these little pins. And there, that's good enough. We need to solder these so that they are, you know, just like everything else, touching one pad, not touching 2, not touching 0. And as you can see, the fact that this is a concave plastic object makes it really hard to manipulate with tweezers. So if you're having a hard time with this, don't feel bad, it's not you. So, using my iron, and I need a new piece of solder. Okay. Solder, iron. Going to do the same thing we've been doing. Heat the pad, make a mound of solder, remove the iron. Great. Now the pad that we've heated up is actually a mechanical retention tab on the connector. If we flip it over, that'll be more apparent. This would be easier with my fingers. Okay, here's the underside of the connector. There's these 2 little fins on the outside. They have no electrical role. They're just reinforcement to make it harder to tear the connector off the board by being overly enthusiastic. And we do like being enthusiastic, don't we? So we're going to make sure we solder them. I'm going to solder them first because they are large, relatively. I mean, they're actually, this is the first thing we've soldered in a while that's bigger than the tip of my iron. And thus are going to be an easy thing to work with for getting this into position. So let me center that a little better. Cool. Grabbing this gently because if you squeeze too hard, it will try to flip because it's shaped weird. We're gonna scooch this over. Ooh. And remove the iron to tack it in place. Now you could probably see there, my hand was shaking through the whole process. It's probably because I took a break and my muscles aren't really expecting to be soldering right now, but I removed the iron when it looked reasonable, and it stopped moving around because the solder hardened and the component is tacked in place. This positioning looks fine. Pins are on pads. It's reasonably straight. Like, I'm happy with this, so I'm not going to second guess myself. I'm going to instead just rotate this to make the other corner accessible to my iron. Still some solder on my iron from last go. Stick my iron in so it's touching both the pin and the retention tab and solder. So let's have a look at that from the side. So here's what we're looking for. You can see the plastic is a little melted from the iron. That's fine. The electrons won't care. As long as the insertion end of this is the right shape, the connectors will go in. This is certainly within tolerance. The solder is flowed onto the pad and the little retention pin. This looks great. Our pins, which are behind my finger looks huge by comparison. Our pins are floating. So the way that I tacked this down, apparently I got our pins floating a tiny fraction of a millimeter above the board. We wouldn't probably even notice this without a microscope, and frankly, it's not going to cause us that big of a deal because the pins are somewhat flexible. That being said, if you run into this and you want to fix it, fixing this should be a matter of putting some pressure on the connector to kind of bend it into the position we want. I'm just going to use my finger. And then reflowing the solder joints. One. Rotate to get to the other one. Smells like burning plastic. Mash the connector down into place. Two. That was the problem. So the first one that I did, it was sitting up. So when I reflowed it just now, it dropped noticeably, like half a millimeter maybe. So since that is now at a different angle from the last time that I flowed the solder joint, I'm going to do this just one last time to make sure it's not holding any stress. And now everything should be good. Let's have a look-see. Zooming in on our pins and moving my focal plane. Oh, that's much better. They're sitting right on the pad. That's what we want to see. And it's a little meltier because we kept reflowing that, but again, it'll be fine. So there, we fixed it. Great. Now we want to focus my microscope. Don't buy cheap optics, kids. Now we just need to solder these remaining pins. So I'm going to work from left to right, sort of arbitrarily. Whoops. You can see what's happening here is my iron isn't actually making contact with the pad or the pin. And so I was poking the pin with solder, and it was just poking. It wasn't going anywhere. So that is not what we want. Let's try, see if I can do this better. Touch, oh, goodness. So I touched both, and look, it flowed. That's because there was enough solder on the tip of my iron to make the joint. Now, this is a thing you can do on purpose. So here I've added a ball of solder to the end of my iron. I'm going to try to do that again. Whoa, holy crap. Here it went. Usually there's only enough solder for things this size for a single pen, but I can add a little bit more. We'll do it again. That one doesn't want to go. There's definitely enough solder on my iron. This might be a case where flux would be useful. So this is a flux pen. It's like a permanent marker, except instead of ink, it writes with a dilute acid that helps to take oxide off of metal surfaces, no pun intended, and make the solder more inclined to go on them. So now instead of the tiny puddle of flux we've been getting from our soldering from the flux core of the solder, we have a giant puddle of flux made by my pen. Flux in general makes solder more inclined to wick on things. So we ought to be able to get that solder to spread out now. Yeah, oh, look at that. That's what we want. And the final pin, it's fluxed, so it should be easy. So I'm just gonna put a little bit of solder on my tip just to be safe. And then, wow, look at that. So I've got some extra solder on here just for aesthetic reasons. I'm gonna clean that up. You can clean up extra solder, generally speaking, by cleaning the tip of your iron and then poking the solder with your iron. It'll climb onto the tip. Okay, so that's J3, our final connector, done. So, how did we do? The USB connector there is it's good. It's got some flux on it. Rest of our components look nice. We got no obvious bridges. We've tested it electrically also, so we're pretty sure there aren't bridges. Okay, at this point we've added the I2C connector, the quick or stemma QT connector, on the end of our board. To know if it works, we need to try I2C'ing through it. So, like before, this is a matter of connecting the device to power. Let's see, it's blinking because our code is still running on it, and that runs whenever we power the device up. We need to connect our debug probe, like so. Incidentally, at this point, we can test our newly installed reset button. See the blinking? If I hold the reset button, it stops. I'm holding the CPU in reset, it's doing nothing. I release the reset button, it resumes. So you can torture your CPU now. Kind of handy. Anyway, this is all connected. We should be able to talk to it through Humility again, but there's nothing plugged into this connector. It's a reasonable place to start. Let's see what happens if we try to use it. So in our Humility install, we had just previously run tasks. So let's replace that with I2C, controller 1, scan. Uh-oh, so we have a screen full of the word error, and it says bus locked. So this looks scary, but I can tell you this is actually exactly what we expect at this point. And the reason is because we didn't install these pull-up resistors. The I2C bus isn't actually working. I2C requires pull-up resistors to keep the lines from being in a arbitrary floating state when nothing is plugged in. We didn't do that. And so Humility is mad and is saying bus locked, which is our I2C driver's jargon for these lines are in an unexpected state and I don't know what to do about it. We can fix that by plugging something into it. So I've bought this evaluation board for a real-time clock. So this keeps time and date, and there's a battery, so it keeps it even if the power is removed. These are useful devices. This was specifically a PCF 8523 I2C real-time clock. So we're going to try to talk to this. Importantly, this board has the pull-up resistors we're missing. They're right here at the end of my finger. Kind of hard to see, but most eval boards that you buy for I2C devices will have the pull-ups on board, and this one is no different. This one came out to 1/10 inch pins, so I've added this breakout cable, which I think I got from Adafruit, that takes it to the little JST quick stemma QT, whatchamacallit, connector that we have on our board. So with this in place, we can plug the thing in. Connector goes in this way, I think. Boop. Okay, that's fully seated. I can't get it in anymore, so that's what it's supposed to look like. Our board's connected. Our CPU is still running, none the wiser. And now, if we go back to Humility and rerun our command, we get, different results. So what this is telling you is I2C devices have a 7-bit address, and we're doing a bus scan. We're trying to talk to every possible address. So in the left column, we have the top digit nibble of the address. In the header across the top, we have the bottom nibble. And you can see we just got a field of boringness everywhere except for this little happy person, which is at 0x68. So I know from reading the data sheet that 0x68 is the I2C address, is one way of representing the I2C address of the PCF 8523 real-time clock part. So that means we have successfully detected it and we are talking to it, and our I2C connector works. So at this point, you could use humility to peek at the registers on the device, check your understanding of the data sheet, maybe figure out the things you would need to write a driver. And then at some point, you'd probably start writing Hubris code to implement a driver so that other tasks on the system could make use of the time and date. But that's out of scope for this video. So we have a working board doing working I2C stuff that we could use to talk to other I2C things in the future. So to take the flux off of the board, I'm using rubbing alcohol. You can also use a dedicated flux remover product, and that's fine. It'll work great. Rubbing alcohol is what I got. I personally have really high concentration, 99% rubbing alcohol, but you could probably also just use the drugstore stuff. It'll work fine. So I'm drawing a little bit of this with a syringe, or trying to. Okay, I'm running low on rubbing alcohol. Okay. Closing this before I spill it or before the fumes kill me. Cool. Now, I have a Q-tip, like you get from the drugstore. You don't really want to use a Q-tip from the drugstore for reasons that'll become apparent soon, but I'm going to. And I have a little bowl, just your average bowl. So I'm going to apply here. I'm going to take my Q-tip, I'm going to take my rubbing alcohol and just like get this to wick onto the Q-tip. There we go. Now my Q-tip is wet and I didn't make a mess. Amazing. So using the Q-tip, we can start over at the USB connector where I remember there being a leak. We can kind of use the rubbing alcohol to dissolve the flux. Now, dissolving the flux doesn't remove it. It's still on the board, but we are dissolving it and making it be a thinner layer, which makes it less obvious. So I'm rubbing over here now. Forgot to bring the camera with me. This is often good enough for basic boards. Just kind of scrape off the flux. So you can see now the rubbing alcohol has dried. It looks a lot better already. Let's maybe make another pass. So if you actually want to remove the flux, you have to wash it. You can do this with distilled water. You can use tap water if you're courageous. Tap water generally won't hurt your boards, but if you're doing anything sensitive, maybe use deionized water. Oh, okay, good. Okay, I was waiting for that to happen. So you notice how it looks like spiders have invaded my microprocessor. This is why we don't use drugstore Q-tips. Or why you shouldn't. I actually do use drugstore Q-tips, but it means I have to deal with this crap. So the Q-tip has shed. There's little pokey bits on the solder, and the Q-tip is prone to, well, being torn up by the little pokey bits. I think that's probably a sign that I've cleaned this board enough. So I'll set the Q-tip aside. So now you can see the board has a little bit of crap on it from the isopropyl evaporating. But if we just rub it with our finger, you could just polish this with a brush or something and it would look much better. And if we're not looking at it through a microscope, it looks quite a bit better. So you might not even notice the flux on the board. So this is our board completed. And yeah. So at this point, we could go through the final test procedures and make sure we did everything right, but chances are pretty good since we tested it at a block level. So I hope this was helpful, and with any luck, you can see that you too can build with surface mount components.